All right, recording is rolling. It is Friday, May 10th, 7 days until the exam. We're going to do more challenge questions. Going to order these posters in front of me. So just for video context here, my first period class, I was proctoring exams, so I didn't have a first period class, but I have uploaded a bunch of links and reference materials to Google Classroom. So hopefully you were able to make good use of your time, get study time there. Okay, but here. Right, so for you guys here, see, we were going through these posters and right, so we did this one last time I saw you guys. We did this one, right? A zero friction incline. Right, now see if you guys remember this. Right, you should definitely get it now. Right, this time, guys. Zero friction incline. Would this block be sliding down at a constant velocity or a constant acceleration? Acceleration, right? It would have to be, right? Right. So, and it could have velocity either way, or it could be starting from rest, and the acceleration would be the same, right? It's this force component, mg sine theta, divided by the mass of the block. Isn't that Newton's second law of motion? Newton's second law, substitute, mass cancels, boom, boom, g sine theta, right? One of the first labs you guys did in this class was rolling Hot Wheels cars down inclines, right? We didn't quite do this level of detail. You guys weren't quite ready for this yet, but in retrospect, you can look back and say, hey, if I had like a 5-degree incline, and I know Earth gravity, you do Earth gravity times sine of whatever, how many degrees from the horizontal, boom. Right, that should be pretty close to what the car was accelerating. Right, so you guys got that one. Right. Now, oh, guys, how many forces are on this block right now? 2, right? Weight straight down and the normal force, normal to the surface, right? Now, switch over to equilibrium. The next one's equilibrium, right? You're going to get some question that involves this. I mean, it's got to show up. Block on an incline, right? So guys, block on an incline, equilibrium. Basically, how many forces? This is 3. Yeah, so the weight straight down, the normal force, say up into the, or is it normal to the surface, right? And also a what force? Friction. Aha. Right. Now, okay, so there we go. Here, show you guys. Right. So you guys can do this, right? In the back of your mind, you're also thinking, okay, well, if I get some question about this, there's a good chance maybe I'll have to think about splitting this weight component, or, sorry, this weight vector into 2 components, right? This angle is this angle, okay? Right. If it's a free response question, just draw those 3 vectors and move on them, right? Okay. Right. Now, this is a link to the next one, though. Next one says sliding at constant velocity. Notice I'm saying constant velocity, not constant acceleration. Guys, constant velocity, could that be equilibrium? Yeah, could be, right? Right. Constant velocity, equilibrium, or well, equilibrium could be constant velocity. Equilibrium could also be at rest, right? But if all you have to work from is the free body diagram, it would be ambiguous. You wouldn't actually know. Right? Right, so let's go constant velocity. And my question for constant velocity, it's the same free body diagram. I just made it smaller, right? You guys see it's the same, right? Right. Is suppose you know what is this angle, right? So suppose I tell you it's 29 degrees, right? It's going around at constant velocity. What is the coefficient of friction between that block and that surface? What's the coefficient of friction? Okay, I think this is about where the bell was ringing last time. Okay. Let's see how far you guys get. Go ahead, try it. Suppose this was a free response, but it might be. Okay. This might be a question you got to say. Free response. And then get as far as you can get. Maybe you'll get the whole thing. Maybe you can pick up 1, 2, 3, 4, 5 points right here. I'm not sure you can do the whole thing. Maybe you can pick up double points. Write down as far as you can get. We're trying to figure out what is the coefficient of friction between that block and that surface. Does anybody happen to have the answer memorized, possibly? Does anybody know what the end result is? What do you think? Yeah, tan theta. Yeah, that's the answer, tan theta, right? That could help, right? If you happen to memorize little tidbits here and there, and you can kind of work backwards from that. Okay, well, what would feed into that would lead to that result? All right. So here, we'll start revealing the answer, but again, hopefully, here, a couple steps ahead of me, right? Maybe you got the whole proof right in front of you, right? So I see something like constant velocity. I think, well, that means no acceleration, so equilibrium, right? So I'd probably write that as my first step or first couple steps, maybe something like that, right? That could possibly be a point, you're indicating to the grader that you understand constant velocity as an example of equilibrium, right? Right. Now, if the block could possibly have motion parallel to the surface, I'm going to look at forces or force components that are parallel to the surface, right? So that's mg sine theta versus the friction. Ooh, wouldn't those have to be zeroing each other out, right? So that's probably the next step, I think. Let's see. Yeah, there it is, right? Friction pulls one way, mg sine theta pulls the other way, that zeroes out, right? I can slide one of these terms over. There you go, just like that. Okay, right. Next puzzle piece. Guys, what do you guys got to substitute in for friction force at this point? There you go. Yeah, coefficient of friction times the normal force, right? Which, by the way, if you're solving for coefficient of friction, it's got to pop up somewhere. Right, so I think it's this next step. I think it's next step. There we go. It is it. Right. Put coefficient of kinetic friction if it's sliding. It could be maximum coefficient of static friction if the block is still locked in place. Right. That would be zero velocity. Right? But kinetic friction. Right. Guys, what's gonna substitute in for normal force? Mg cosine theta. Boom, boom, just like that. Right. Okay. Now this might be the end step right here. Right. Because I see an mg on both sides. So the mass of the block didn't matter. The gravity field for that matter doesn't matter, right? You could take this whole system to the moon. I bet you get the exact same results, right? Mu is tan theta. All right, you guys remember that? All right. So you guys get that question. There you go. Okay, guys ready for our next one? Okay. All right. Let's see what I got next here. Ooh, truss joint in tension. Here, maybe I'll just show you guys this one. Right. So suppose you have a weight pulling straight down, you got a couple of scales pulling off at some angle, right? This is that kind of simple one where maybe by symmetry, these look like the same angle, right? Now, in college, be ready to solve for all these individual forces. So if they give you angles and they ask for what's the force in the spring scale, right? Now this particular class, AP1, I doubt they'd ask that. Maybe they might ask something conceptual like if this angle changes, does the force increase or something like that, right? And maybe you could use this, right? But here's the guiding principle, right? Whatever kind of question you have to field, here's the guiding principle, is that the sum of the forces go to zero, and that's true in each direction. So in the horizontal, that's true, and the vertical, that's true. You guys see, there's really three forces here, the weight down and there's two spring forces, right? And do you guys see that the horizontal components of the spring forces zero out, right? This one pulls right as much as this one pulls left, right? If I change this angle, that'd still be true. The horizontal components would stop zero out, and the vertical components zero out. So these spring scales are collectively pulling up, and up as much as the weight's pulling down. That's what that says, right? Right. And then there's like 20 different questions to get asked branching off that, but that's the guiding principle right there. Okay, you guys feel that? Right. Yeah, I don't have all my posters here, but just try to pick ones that would be most likely for you guys to see here in 7 days. Okay. Do you guys remember this? Got vertical loop, free body diagram. Let's say this could be a ball on a string. This could be, I think back in the day, I put some water in a cup, also attached to a string, and I was wheeling that around in a vertical circle. So vertical loop, right? I might say side view, right? Here's the question for you guys. Guys, what is the minimum speed to get around the top for a ball on a string? What's the minimum speed for it to stay in that circle pattern? Go ahead and derive that from scratch. Drive it from scratch. What's the minimum speed to get around the top? Because see, if I had that water in that cup and I was flying it around too slow, then the water's going to fall out, right? Or if it was a ball on a string, maybe the here we go. I got a model right here, right on the top, right? Right. I don't want the string to go slack. Maybe that's a hint. String tension. Right? Hopefully you know what you're doing. You need another hint. Guys, if I'm talking about string tension, does that sound like it's probably something more related to forces in equilibrium, or probably something more related to conservation of energy? What do you guys think? I think probably forces, right? You guys think? See, it's in a circle pattern. Hey, what do you guys know about forces involved in something in a circular path? Okay, yes. So about net force, maybe, right? They're trying to figure out what is the minimum speed to get around the top in terms of variables. Notice that there's no numbers here, right? But let's see, there's some gravity field, there's some mass of the object. You know what variable I don't have listed here is the radius of the circle. Guys, that's part of the answer, the radius of the circle. Okay, you guys got that? Right, so this radius matters. Right? If there's a little circle versus a big circle, you need different speeds to get around. Okay? Or maybe by this point, you possibly have the answer just memorized. Of course, you have to show your work, but it's a free response question. Right? Who knows? What's the answer to this question? What's the minimum speed to get around the top? Who knows? Who knows? Ooh. Ah, there you go. That's it. Yeah, square root GR. That's the answer. All right. So let's see. What's the process here? I'm going to go with okay, so net force, yeah, you guys were mentioning net force. So I'm looking at the top. What's the net force? Say, well, I really got possibly these two forces both pulling downward, right? Collectively acting as centripetal force, wouldn't it be? Right. Now, if the question is the minimum speed to get around the top, minimum, then what can you say that this tension force is approaching? Zero, right? Approach zero. Right? It'd be like minuscule, right? So I'm going to go ahead and let that tension force go to zero. Get rid of that, right? Okay, so only the weight of this object would be keeping it on a circular path, right? And that net force would be acting as centripetal force. So I substituted in V squared on R. Right, you guys got that? Right. By the way, I pointed this out many times, so I think you guys got this by now, but AP does not actually list centripetal force. They do list centripetal acceleration as V squared over R. You guys remember that? It's kind of near the top. Right, so you guys got that? Boom, boom. Right, so you could solve for V in the minimum top, and there you go. That's good. All right, guys, good. Spirit GR. Okay. Good one to know. Right. Ooh, all right, we're moving on to unit 3. You guys ready for unit 3? Right. So looks like first poster I got here is gravitation. Now, here, I bet everybody knows this, right? Maybe I should ask you guys, but you guys would have written that down. I think it was GMM over R squared. It's Newton's universal law of gravitation. There were a few topics all put together in this unit 3. There's universal gravitation. There was circular motion. Actually, that was kind of what we did here, right? This is actually kind of unit 3. Maybe I should put this in unit 3, right? And then, and there was orbits, right? You can put those two as make orbits. So we're gonna do a little bit of each of that. Also, I think I have a scaling question coming up pretty soon too. Okay, what's next here? Okay. You guys remember this lab? I reference this lab all the time. Here. Well, let's kind of skip through this. Okay. So you guys definitely could have come up with this, right? Centripetal force, mv squared over r. In this case, is provided by this tension, which is equivalent to this weight that's hanging. Boom. Just like I did to your lab. Centripetal acceleration. Boom. You guys got that? Okay. You're gonna see this on the exam. Okay. This is gonna come up. So you guys ready to do that? Okay. Now, here, I did also throw in this. Less likely that you'll see it. You probably won't see this, but I don't know. You could. Right. What if you have like a rigid turntable or something, right, that where it's all moving together, right? Then it's probably more convenient to approach this from angular velocity rather than linear velocity, right? So you multiply by r rather than divide by. Right? A little substitution there. Right. All right. Ooh. Right, guys, this one. All right, let's drive this one. Drive orbital speed from scratch. Go. So suppose that was your free response question. And okay, set up some kind of context out. We're going to send a probe out to some distant planet X, which has so many times the mass of Earth and so many times, right? Or you got to figure out what's the orbital speed. We're trying to get this probe to be a satellite of this planet we're exploring. To revolve around. What is the orbital speed? And then free response question, you have to show all your steps, derive the whole thing from scratch. What is orbital speed? Give you guys a hint. And your answer is going to be universal gravity constant, the mass of the planet that's being orbited, and the radius of orbit from the center of the planet. There's probably a good chance that you probably have this memorized anyway. Guys, what's the answer to that question? All right, I'm seeing a few guys say square root GM on R. Yeah, that sounds it. Right? Boom, just like that. Right? So you're letting the gravitational force act as the centripetal force, right? Here's universal gravitation, gm on r squared. Here's centripetal force, mv squared on r. Some stuff canceled. Hey, ooh, the mass of the satellite cancels, right? Little m goes away, right? Right, so, okay, there you go. Orbital speed, boom. You guys remember, too, you're not going to be asked about escape speed, but do you guys remember what is escape speed compared to orbital speed? Right, you just slip a little 2 under here. Right, right. You can show that from conservation of energy, but they're not going to ask you that. Right. Scaling time, scaling time. You guys remember this poster right here? Right, it's scaling time. Oh, I can almost guarantee one of the questions you're going to get is some version of, there's a planet that's so many times the mass of Earth and so many times the radius of Earth. What's the gravity field of that planet? Right, you guys ready for that? Okay, I'm just gonna make up something on the fly here. Let's say the mass of planet X is 7 times the mass of Earth. And let's say the radius of planet X is 3 times the mass of Earth. Radius. Whoops, sorry. Thank you. Whoops, I'm so sorry. Yeah, good call. 3 times the radius of Earth. Yeah. All right. So question is, what is the gravity field on planet X? Right. Now, I have not solved this ahead of time, so I'll solve it off screen. You guys solve it. Second. Okay. So here. All right. Let's see what we get. All right, I got the answer. Who knows the answer? Who knows the answer? Who's got it? What do you think? So, some a little different, I think. Here's oh. Hey, how many what's the unit for gravity field? You got 2 options. You could do meter per second squared. You could also do, what's the other one? Newton per kilogram, right? You do like that? Okay. All right. Okay. Show you guys my solution here. Okay. So I'm going to start off with, what is an expression for a gravity field? So gravity field, let's say I got a little subscript Earth here. Okay. Got gm on r squared. Okay. Notice I left off the second mass. If I throw in another mass here, that would give me a weight, wouldn't it? Right. So gravity field at the surface of any planet is gm over r squared. Okay, where r is the radius of that planet. Okay. So you guys got that? Okay. All right. Now, okay, and I know a value for that for Earth. Right, so I'll jot that down too. I'm going to round it a little bit. You can do 9.8 if you like, and do 10 meters per second squared. Okay. Now we're going to do for planet X. So I got gravity field on planet X. Now we're relating everything back to Earth. Right? So we're doing proportions here. Right? So I told you 7 times the mass, boink, that's right there. I told you 3 times the radius, boink, that's right there. Now the mass is a direct factor, but the radius is being squared. Right? So don't miss that detail. Right? So here's my factor 3. But that's being squared. I'm going to pull that out in front and the 7 out in front. That gives me 7 over 9, right? Times, and then this expression represents Earth gravity field. Boink. That's that right there, right? So it's 7/9 of Earth gravity. So 7/9 times Earth gravity, right? It's about 7.8 meters per second squared. You can say 7.8 Newton per kilogram. Right, you guys got that? Right. Ooh. There's a harder version of this, which is, what if the planet was made out of the same density material, right? And also assuming uniform density, a little simplification, right? Now for that, there'd be some extra steps because you have to, here, I want to kind of show this to you guys, right? This one's a little tougher. You more likely to see this one in college, right? Is I know that density, let's say like the density of Earth dirt, well, okay, that's like mass per unit of volume, right? Mass per volume, right? Capital V volume, right? And that breaks down into, well, what is, see, mass is already related to volume. The more volume, the more mass. So I'm going to replace mass, or wait, how am I thinking about this? Density, but okay, right? For some given material, some density, right? These two are related. Let me do, let's do mass equals density times volume, right? You might have to, okay, so I have to break, oh, I remember where I'm going with this, right? I want to connect this volume back to radius. That's what I'm trying to get at, right? So volume is proportional to the radius cubed, right? And if you want something a bit more exact, you could say the volume of a sphere, right? So mass equals, see, density of the material, right, times, does anybody know what is volume of a sphere in terms of radius? It's like 4/3 pi r cubed, right? Now you don't have to know the 4/3 pi to get this proportion question right, right? As long as you know volume is proportional to r cubed, they'll still get you to the straight answer, right? So use something like this. Now again, if we're comparing planets, we say suppose it's made out of the same material, right? This density times 4/3 pi is all constants, right? And then you could say, okay, since the volume is proportional to the radius cubed, the mass is also proportional to radius cubed. Use something like that. Okay, right, guess that. Okay. In your college notes from way back in the day, I saw one that's more along those lines, a little bit more complicated. All right, here we go. Oh, I remember what else I was gonna say about this. Right. So what about the planet that I just made up on the fly here? Right, where you have 7 times mass Earth and 3 times Earth radius. Right. Notice when we solve for gravity field, we got, what was it, like 7.8 Newton per kilogram, something like that. Okay. What is this planet made out of? Guys, is this planet made out of puffy styrofoam or really dense lead? What is this planet? Here, it's one or the other. Is it styrofoam or lead? Let me see, show of hands. How many guys say styrofoam? It's a puff planet styrofoam. Yeah, yeah. Here's how you know. Because 3 times the radius of Earth, right? That's kind of connected to this right here, right? Is how many times the volume of Earth? 3 times 3 times 3 is 27 times the volume, right? Even if you include the 4/3 pi, when you divide it out, that part cancels out, doesn't matter, right? Yeah, so it's 27 times volume, right? So all else equal, like equal density, it should be 27 times the mass, but it's not. It's only 7 times the mass, right? That's not nearly as massive as it should be, right? Maybe it's about a quarter of the density, right? Right, approximately. Okay, so that, yeah, so definitely a styrofoam planet. Oh, yeah. Okay. All right, so you guys good with good scaling there. Okay. Ooh. I'm curious to see how many guys gonna get this next graph. Right. So let's say what's the gravity field in the proximity of a planet. Right. So I've got a set of axes started. Put gravity field on the vertical. Put radius or some radial distance from the center on the horizontal axis. Right. And let's say you're allowed to dig inside the solid planet and go tunnel all the way down to the center if you want. Okay. Right. And then you can go back to the surface, and then you can take climb a really tall tower and then like fly off in a rocket. Right. Right. So at the surface, let's say this is Earth. At the surface, you know, it's 9.8 meters per second squared. Right. So the further away from Earth I get, I know it's gonna taper off 1 over the distance squared. I know right at the center it should like zero out. Right. Do you guys remember what this graph looks like? We got covered up. Okay. Put my sound room. Here, see, you can get this. Okay. Okay. You guys got parts of this right? Parts of it. Okay. All right. Let me show you kind of exactly what I'm looking for. Okay. I just something like this. All right. So I have some generic distance from the center, lowercase r, and I have a special capital R for the fixed radius of the planet. So if you're on the surface, boom, for Earth, that'd be 9.8 meters per second squared. Okay. As you tunnel down to the center, okay, it eventually reaches 0 right at the center. Okay. And then fly off in a rocket, it's 1 over the distance squared. Just like that. Okay. There's that. Right. All right. Ooh. This next one, this one right here, I've seen AP ask questions about this. I think there's probably a 50-50 chance you're going to get a question about this conical pendulum, right? Now, AP likes to keep it conceptual. So the kinds of questions they asked about this are something like, they might want you to draw a free body diagram of this object. Notice it's going around the path of this object is a circle. And if you include the string, then it looks like a cone, right? I see like a conical pendulum, like a cone-shaped pendulum. Right? So it's just going around. So you could call it constant speed, that'd be good. Right? Constant tangential velocity. They might say, draw the free body diagram. If they ask that question, how many forces are on that object right there? 2. The weight straight down and the tension force up to the left. Or okay, up at some angle. That's it. That's the only 2 forces. Okay. Now, if you want to do extra analysis, then you're going to have to introduce a Cartesian system and align these vectors. Usually how you do it is Cartesian system could be just simply aligned to gravity field, so straight vertical, straight horizontal, in which case you'd want to break this tension into components. Okay? And you'd say the inward pulling component would be acting as the centripetal force. Notice I have it labeled net force. That's what this is right here. Net force is acting as centripetal force. Is that right? I've got dashes all over the place because you could remember there's only 2 vectors. Boom, boom. These 2 right here. Right? You could add them tip to tail, and they would still give you this as the resultant. That's what net force is. Or it's the resultant of all the forces put together. Right? You guys get that? Right. There. And then here, you might have to do this type of analysis. So here's the setup. Right. See, playing off this angle from the vertical, right? That's important for getting sine or cosine correct. Right. So from the vertical, see, tension times cosine theta, right? That's this component right here, minus the weight down has to 0 out. So this object's not moving up or down, right? And then Ft sine theta, which is this component right here, is the net force, which is the centripetal force. Right? So you guys can navigate conical pendulum. All right. Ooh, next one. Guys, write down the 3 rotational kinematic formulas. Ha. So you can get these. How you guys do linear the other day? See if you guys can get the rotational versions. Rotation. This would be like if you have a turntable, it's like, okay, say it turns so many radians after so many seconds. Maybe it's speeding up or slowing down how it's rotating, called angular acceleration, possibly. Anything like that. Okay. Now remember, these look just like the linear kinematic, but for angular. Right? So say you have a turntable. Right, here we go. Here's our. I'm gonna put these side by side. Wow, got so much screen space, but here's your linear versions. Boom. Right, here's the rotation. Right. So how far does the turntable turn? Angular velocity, how fast is it rotating? T, how much time? Alpha, angular acceleration, would be speeding up or slowing down, spinning. Okay. Right, boom. Boom. All right, so you guys got this? All right. All right, what's next? Oh, yeah, this next one. This is good to know. How do you translate back and forth between linear motion and angular motion? Right, just very simply multiply or divide by the radius, depending on which way you're going. You guys do that? Right. Take radians, multiply by meters, they'll give you meters. Take x in meters, divide by the radius r, they'll give you how many radians it's turned. Okay, something like that. And how far is this point moved? Right. Well, there's an answer in meters, but there's also an answer in turntable radians. Right. Ooh, guys, how about this? You guys see these 3 points right here? These 3 points. Suppose this turns from here to here. That's approximately 1 radian. What you're looking at? I think it's a little short of 1 radian. Right. Do all these 3 have the same angular displacement data? Yep, they all just move 1 radian. Do they all have the same distance x moved? No, the middle one didn't move at all. Right, in terms of linear, right? This one moved, some distance, right? And then this one moved further, right? In fact, this top formula, you guys have known a specific version of probably since elementary school. You guys know circumference equals 2 pi r. Right? That's a specific version. Okay, so you guys know. All right. Ooh, let's do some graphs. You guys ready for graphs? Graph time. Oh yeah, graph time. Let's do turntable slows to a stop. And I got 3 graphs lined up. You got theta, omega, and alpha, all as a function of time. Okay, turntable slows to a stop. So you give it a spin, yeah, maybe there's a frictional torque, and after like 30 seconds, it slows to a stop. Here's a hint. If you turn this into a linear problem, the graph would look just like a car braking to a stop, right? Same looking graphs, right? Let's do that. All right, let's check these out. Okay. So let's see, slowing to a stop, right? If I start with the middle graph, see there was some angular velocity at the beginning of the interval, and that slowed down to comes to a stop after some time, right? Now in this class, with some very rare exceptions, you're always going to assume uniform acceleration. That's why this is a straight line, right? So it slows down at a constant rate with respect to time. Okay, so get that, right? Okay, and the slope of that represents angular acceleration, which is, like I just said, a constant value. Therefore, alpha versus t is constant. It'd be negative slowdown. Okay. Now, the kind of tricky one is, well, how far theta in radians did this thing turn as a function of time, right? If you think about it, suppose I split this up into like 3 intervals: the first interval, the middle interval, and the last interval, right? Well, the first interval, it was spinning really fast. So for some given interval of time, it went a long way. Then the second interval of time, well, that's not moving as fast, so it's not going to go as far. And then that last interval of time where it's coming to a stop, it's going really slow as it's coming to a stop. So didn't turn hard at all, right? Because what shape is that right there? Parabola. And there's the vertex. I'm pointing at the vertex of that parabola right there. Boom, boom. Right? All right, what's next? Ooh. Well, here, I'll just show you guys this one. Okay. Car turns on a banked track. Okay. Now, if you're in college, know this whole thing. AP is, if they ask you this question, they're probably going to stick to something conceptual like draw a free body diagram. Now we draw a normal force and a weight. Guys, notice for this one, a car going around a big curve. It's going into the paper. Which force is larger magnitude, the normal force or the weight? The normal force. That's different than if there was a block sliding down an incline. Normal force was mg cosine theta, and it was always less, right? But that's not what's going on here, right? Going around a big curve. And you know that because if you're sitting in the car, you feel really heavy, right? Don't you feel really heavy going around a big curve, right? Right. So for example, right. And then AP might ask something like, what force is acting as a centripetal force? And it might be multiple choice. And the answer would be the horizontal component of the normal force. Actually, I've seen that exact question before, and that was the answer. Okay. Turntable friction. Here, this will be the last one. Oh, yep, it's gotta be the last one. All right, last one. Okay. Suppose you get this a spin, and this here, suppose you got the slug right here, right? And you spin this up faster until it's just at the breaking point. And if you spun it any faster, it would fly off, right? So what is the coefficient of friction between, say, this slug and this turntable surface? Can you solve that, right? So okay, I had you guys do this lab too. This could be a question. AP could ask you that. Here, I'll show you guys that. I know yesterday you guys were relocated. Sorry, it's a last minute thing. First got testing season, right? I think did Max give you guys these papers yesterday? I think, right? You guys get these, right? Did anybody not get these? Maybe was some paper short. Here, let me get you some of these. Right. So, you guys are getting that one in your notes. Right, that turntable question is good enough. Right, does anybody need these 2 papers? These 2 papers. Okay, who else needs these 2 papers? These 2 papers right here. All right. Right. So again, what we're looking at here, got the AP equations, which is actually 2 sides. I usually refer to the side, but don't forget there's the side 2. Right, so you guys got that. Right. And this other page I gave you on the very first day of school when you guys walked in here, right? Tells about here, got unit 1 through 6 on the front, got unit 7 on the back, and also some extra stuff that got bumped a few years ago. Got vectors and trigonometry, got some reference stuff about vectors and graphs stuff, right? Guys, it's all here. Yeah, this has some nice examples, right? When to know that context, key formulas, some key examples, some key graphs, boom, all here. All right, there's our ghost bell right there. All right, you guys have a good day, or have a good weekend. Yeah, I'll see you guys on Monday.